This is the technical blueprint of an AI OS runtime environment. It is designed to manage deterministic on-chain operations within an isolated core, ensuring that data ingestion and state transitions happen within a single, secure environment. By executing these functions at the system layer, we eliminate the need for human intervention. This removal of latency allows for the deployment of financial infrastructure in regions where manual processing is either too slow or too unreliable to scale. In this tutorial, we will execute 3 core deliverables. First, we will construct a deterministic state machine. Next, we will natively integrate a domain-specific small language model directly into the runtime. Finally, we will establish an automated liquidity monitoring loop to protect the ledger. Before we begin, ensure your environment is prepared. You will need a configured testnet IDE, active Rust and Solidity environments, and a pre-trained SLM binary ready for deployment. Completing this baseline architecture transitions your workflow from deploying isolated smart contracts to engineering a system that manages state and executes logic independently. Let's initialize the workspace. Step 1 is establishing a strict architectural quarantine. We must provision a sandboxed execution environment to isolate rogue smart contracts or unverified testnet oracles. To build this, we initialize a memory-safe Rust workspace. This boundary ensures execution errors cannot escape the runtime node. Inside, strict cryptographic data structures enforce absolute rules, ensuring the OS follows programmed protocol without deviation. To verify that resource isolation is active, check your terminal output. Look for the successful cryptographic handshake confirmation before proceeding to the next step. This setup ensures that your core system remains unaffected by the performance or security failures of the external contracts it interacts with. Next, we build the finite state machine. It governs autonomous transactions, moving from state A to state B only when logic gates are cleared. Specific solidity parameters control this move, blocking transition unless every condition is perfectly satisfied. You must lock down this pathway completely. Configure the smart contract so state transitions happen only when programmed parameters are explicitly met, preventing unauthorized changes. Governing transactions through a finite state machine guarantees deterministic execution, removing the risk of subjective error from the transaction flow. Now we automate transaction oversight. We import a domain-specific small language model directly into the core OS to handle parsing complex liquidity vectors. This SLM must run entirely locally inside your sandboxed environment. Notice there are 0 external API calls. This ensures sensitive transaction data is processed without leaving your sovereign architectural boundaries. Next, we write custom parsing logic, commanding the SLM to track cross-border liquidity vectors. The model constantly reads variables to maintain high transaction speeds, simultaneously mapping every operation against strict on-chain compliance metrics to ensure validity. Embedding the model locally shifts it from a passive tool into an active part of your execution engine, capable of making parsing decisions in milliseconds. The final core OS piece is the defense mechanism. We code algorithmic monitoring loops into the engine to actively track live liquidity pool depths. This chart tracks our live liquidity pool. Within this loop, we program explicit threshold parameters, represented by this horizontal line, which define the minimum safe collateralization ratio for the ledger. We script an autonomous defect repair function to enforce this. If metrics fall below the line, it triggers an auto sweep. In our simulation, as valuation drops below the threshold, the system instantly triggers a corrective spike, restoring the balance. This successful simulation demonstrates that the engine can execute corrective sweeps the moment a specific parameter is breached, without waiting for human administrative clearance. Let's review the completed baseline. The runtime is isolated within the memory-safe boundary, and the finite state machine is actively processing deterministic transactions via the native SLM. Simultaneously, our continuous algorithmic monitoring loop is now actively protecting the entire ledger system through automated risk auditing. You have successfully engineered and deployed a fully autonomous, memory-safe execution engine on your testnet. But an operational OS is only as powerful as the data it processes. To fuel the system with real-world inputs, click on screen now to proceed to video 2, where we build the Layer 2 physical-to-digital ingestion bridge.